So we just have seen how to decompose the AllDifferent constraint. The goal now is to make this decomposition a little bit more efficient. And for that, we will use a global constraint that is able to achieve exactly the same filtering, but in a faster way. Let's first consider what happens whenever a variable is fixed. Whenever a variable is fixed, like this one, or this one, then you can remove it from the domains of the other variables. So as a consequence, you can see here that 1, 2, and 3 are already decided, assigned to some variables, so we can safely remove them from the domains of the other variables, x1, x3, and x5 in this case. This is the filtering that is also performed by the forward-checking reasoning for the AllDifferent. Whenever a variable is fixed, you remove it from the domains of the other variables. What happens in terms of time complexity with the decomposition is this. You realize that one variable is fixed. For instance, the variable x2 is fixed to the value 2, and then it will trigger the filtering of all the other binary constraints that are attached to that event that we're interested to be notified whenever x2 was fixed. It means all the other variables, and so you will consider the removal of the value 2 from x1, x3, x4, x5, x6, x7, x8, x9, okay? And it takes theta of n time complexity to scan them all, just to realize that maybe it was not so useful, because since x3 was already fixed, clearly it's impossible to remove the value 2 from this variable, okay? But still, we have spent a time that is proportional to the number of variables in the constraint, and what we would like to pay is a time proportional to the number of unfixed variables. How to do that? Well, the trick is the same as for the sum constraint. We will use a sparse set that will split the fixed variables from the not fixed variable, and for that we will use a state integer n fixed that is equal to the number of not fixed variables in order to implement the sparse set. And to maintain the separation between the two, every time the propagator is triggered and the propagate method is executed, we will scan starting from the index not fixed until the size of the array x, okay? So we scan here all the not fixed variable, and if we detect that one of them is fixed, you swap it just before the index of the not fixed value. You swap it with another variable that was that you know that is not fixed, so that the invariant is true. You clearly keep the separation between the fixed and the not fixed variables. And at the end, you update the state integer to the new not fixed number of variables. So visually, this is what you have. So you have separated the array of variables in two. You have the fixed variables and the not fixed variables. And the forward checking algorithm, we only consider these variables. These one, they are fixed, and we know that they are all different. Okay, so we know that all these values taken by these variables are different, so we are already satisfying the constraint there. Okay, and all these values that are fixed, they have already been removed from the variables in the not fixed set. So when the propagate method is executed, we will scan starting from there all the not fixed variables. Okay, so we have a double for loop, if you want, for each variable xi in the not fixed set. If we detect, for instance, that one of them, this one for instance, is assigned to some value v, okay, xi at index I is assigned to the value v, then we will remove v from the domain of the other variables in the not fixed set, and that's very important. Okay, we will not consider again the removal from the not fixed from the fixed just detected fixed variable I towards a fixed variable, because we know that these ones are already safe. We only have the loop here that consider the not fixed set. And so the time complexity for this, clearly you have an iteration in the outer for loop, and whenever a variable xi is detected as fixed, you need to remove this value from the domain of all the other variables. So it means a time complexity of the order of the not fixed variables to the power of 2. Okay, so that's not fixed to the power of 2, and that's much better than n squared, of course, because in most of the cases, as we will see next, this set is quite small in practice. Okay, in practice, most of the variables are fixed, and most of the time you will spend it there. Okay, with a very small set of not fixed variables. And the reason for that is that most of the backtracks that we'll do when exploring the search tree will happen in the bottom of the search tree with a large part of the number of variables, okay, that is already fixed. Okay, that's the majority of the time you will spend it there with a very small number of not fixed variables. I did a small experiment just to confirm this intuition. So I experimented on the 15 queens problem, and on average, when I was measuring the number of not fixed variables for the 15 queens problem, whenever the propagate method of my forward checking algorithm was executed, there was on average 10.86 variables that are already fixed in the scope of the AllDifferent constraint. So you see, there is less than 5 variables that are not fixed. So it means at least 2/3 of the variables are already fixed. Okay, this is why it's important to consider to have a filtering algorithm that is optimized to only consider the not fixed variables. So, does it help? So let's consider again the experiments there and measure the time that it takes to solve the n queens problem. So for the 15 queens problem, I experimented with 2 different types of configuration. The first one was using the binary decomposition. So you have the n² binary constraint not equal constraint, and you have the global constraint using the forward checking algorithm using the sparse set. And in terms of time, I have 43 seconds compared to 63 seconds with the binary decomposition. So that's the speed up that I have with the trick of the sparse set. But that's for 15 queens. So it means AllDifferent that are expressed with a range of 15 variables. Let's enlarge a little bit the problem and consider more variables to see if the speed up is even more consequent, more important. So I have now an experiment with 30 queens, and now the speed up is even larger, right? You see that the speed up there is almost 91%, okay? And then for the 60 queens problem, I was looking for the first 100,000 solutions because trying to discover all the solutions there would take a lot of time. And I stopped after this number of solutions. So the 2 configurations will exactly explore the same search space because, again, they have exactly the same filtering, but one of the 2 is a little bit faster because it only considers the not fixed variables. And as you can see, the speed up is even more important in that case. So it really pays off to do that, to use the trick of the sparse sets and implement the forward checking algorithm using an optimized version that only scans the not fixed variables incrementally. And this is what you will do in one of these assignments related to this lecture.